Rising 232 meters above the Taronga harbor, Mauao is a dormant rhyolitic lava dome situated directly adjacent to dense coastal infrastructure. Its structure consists of an extremely strong core of subvertically jointed rhyolite bedrock, tightly wrapped in a highly weathered mantle of volcanic ash and colluvium. In January 2026, an extreme weather event dumped 300 millimeters of rain on this profile in 48 hours, triggering 42 simultaneous landslides across the dome. These failures initiated as shallow translational soil slips, but rapidly converted into high-velocity debris avalanches carrying massive rhyolite boulders downslope. The resulting mass flows overran the high-occupancy base track and destroyed infrastructure in the Mount Manganui beachside holiday park below. Securing this terrain presents a unique mechanical challenge. Standard massive gravity retaining walls are structurally and spatially incompatible with this specific geological environment. Effective stabilization requires engineering systems that directly counteract the mineralogical fluidisation of the soil and actively dissipate kinetic energy upon impact. Effective containment of these sensitive soils requires a shift from brute force structures to systems that directly manipulate the micromechanics and internal physics of the slope. The primary failure vector on Mauao is rapid rainwater infiltration, which drastically alters the internal effective stress of the soil mantle. This diagram illustrates the Moore-Coulomb equation, calculating shear strength based on cohesion, normal stress, and internal friction. As rainfall saturates the ground, surging pore water pressure eliminates matrix suction. When effective normal stress drops, shear strength plummets toward zero, initiating a slide. The severity of the Mauao avalanches is dictated by the specific mineralogy of its volcanic mantle, which is dominated by halloysite clay. Microscopically, halloysite consists of hollow tubular crystals. Under ambient conditions, these tubes interlock, providing high peak friction angles to support steep slopes. When a slide initiates, mechanical force shears the tubes apart, forcibly aligning them parallel to the failure plane. This sudden structural breakdown triggers rhyological fluidisation. The apparent residual friction angle of the soil drops from 37 degrees to as low as 10 degrees. Because halloysite is extremely sensitive to remolding, the physical shear transforms the stiff clay into a high-velocity, low-viscosity slurry. The volcanic soil physically changes state, from a solid to a liquid under stress. Static gravity walls designed to retain dry earth are entirely mismatched to contain an incoming fluid wave. The traditional engineering approach, mandated by standard retaining wall design modules, relies on rigid, passive containment. In steep erosion gullies, this typically involves constructing massive, reinforced concrete Sabo check dams designed to block incoming debris through sheer structural resistance. The hydrodynamic impact equation calculates that a slurry surge at 10 meters per second generates over 300 kilopascals of dynamic pressure. Resisting this kinetic energy requires deep foundations that would destroy the sensitive archaeological Wahitapu sites on the mountain. Moving from the gullies to the lower slopes, the geometry creates a different set of physical constraints along Adams Avenue and the public base tracks. To meet stability requirements, a standard 2.5-meter-high unreinforced catchment bund requires an 8.5-meter base footprint. The available corridor between the slope toe and the urban boundary is frequently less than 3 meters wide. Rigid structures are disqualified on two concurrent fronts. They cannot safely absorb fluidized kinetic energy without massive scaling, and their required geometric footprints violate local spatial and cultural constraints. The engineering strategy must pivot away from passive containment at the toe of the slope. Hazard mitigation requires active prevention directly within the initiation zones. On the upper subvertically jointed rhyolite bluffs, the optimal solution is an active pinned high-tensile steel wire mesh system. Unlike loose drapery netting, this mesh is bolted against the rock face under continuous pre-tension. Applying 150 kilonewtons of active lateral force per meter prevents the initial joint dilation and block detachment that causes rockfalls. Securing this mesh requires specific anchor mechanics. The drill path bypasses the outer 3 meters of weathered rock to secure a 1.26-meter bond length deep inside the solid, competent rhyolite. For the soil mantle, stabilization targets the root hydrogeological driver, saturated pore water pressures. The primary mechanism for this is a network of subsurface horizontal gravity drains. High-durability pipes, 100 millimeters in diameter, are drilled up to 100 meters deep into the hillside at a slight upward incline of 2 to 10 degrees. These passive relief wells drain perched aquifers, lowering the water table via the Dupuit-Forchheimer elliptical drawdown curve. Because the volcanic ash has low hydraulic conductivity, pipes are installed at tight 5 to 8 meter intervals, ensuring the drawdown zones overlap. By mechanically clamping the outer rock mass and continuously bleeding internal fluid pressures out of the soil, these subterranean systems artificially guarantee the slope's mathematical stability before a storm arrives. In the steep debris chutes where failures cannot be entirely prevented, the resulting channelized flows are caught by high-energy, flexible steel ring net barriers. The critical engineering component of these nets is the inline U-brake energy dissipator, attached directly to the boundary support ropes. On this force time graph, a rigid wall absorbs a massive instantaneous force spike. The flexible net produces a significantly lower, extended curve. As debris strikes, U-brake rings to form plastically, extending displacement. This drops peak transient forces by 80%. The nets also perform a vital secondary hydrogeological function by rapidly dewatering the debris. The porous steel ring structure allows the water phase to pass through instantly. This consolidates the highly mobile slurry back into a stable, dry granular mass that exerts minimal static earth pressure. Yielding to the surge through controlled plastic deformation neutralizes its kinetic energy while simultaneously draining the fluid phase, providing a stable containment structure that remains within the mountain's physical and cultural constraints. To mathematically validate these interventions, engineers apply a quantitative risk assessment, measuring the individual annual risk of fatality. For the high-occupancy base track, the unmitigated spatial temporal exposure generates a risk level exceeding 10 to the negative 3. This is well above the strict 10 to the negative 5 legal threshold required for public zones. Combining the active slope stabilization structures with a real-time automated sensor network drives that probability factor down, achieving regulatory compliance for public life safety. The final variable is the 50-year life cycle cost analysis, comparing the intrusive rigid structures of option A against the integrated low-impact systems of option B. This data table reveals that option B yields $1.5 million in savings. This efficiency is driven by avoiding heavy earthworks, utilizing modular helicopter logistics, and the 50-year survivability of zinc-aluminum eutectic coatings in a severe coastal marine environment. Modern geotechnical stabilization balances the mountain's geological instability and cultural significance through precise mineralogical intervention, dynamic energy absorption, and rigorous life cycle economic modeling.
Welcome to AI Documentary.